Hello? Hello? Okay. Hey, everyone. All right, let's get started. So I'm Jacob. I'm a researcher at Veradice, and today I'll be telling you about Medjai, one of our formal methods tools we've developed for zero-knowledge programs. First off, let me concretize what I mean when I say formal methods, because this term refers to a wide variety of different techniques. We consider formal methods to describe any technique for automating reasoning about the correctness of programs. Along the spectrum, from left to right, these automated tools can provide stronger guarantees at the cost of more human effort. And to be clear, when I talk about formal methods in this context, I'm not just referring to a single technique or tool on this slide. Instead, I'm referring to a class of techniques including systematic testing, static analysis, and formal verification. For our specific domain in this talk, which is zero-knowledge smart contracts, we use formal methods for the purpose of both finding bugs and constructing proofs about the correctness of programs, indicating a lack of bugs. For example, automated testing has proven able to uncover bugs that handwritten tests are not likely to find, while formal verification can prove guarantees about code correctness. Today, I'll tell you about Medjai, which sits in the formal verification bucket. At Veradice in general, though, we also make other tools for both static analysis and automated testing over a variety of domains. Let me give you a bit more detail about Medjai specifically. Medjai formally verifies Cairo smart contracts by using a formal methods technique called symbolic execution. Given a Cairo program and a high-level specification written in a language called V, Medjai either reports that a program fully satisfies the specification or reports that the program failed to verify with an explanation of that failure. This explanation comes in the form of a concrete input that causes a bug. The main downside to using Medjai here is in the complexity. Since Medjai must reason about all possible program executions, it's possible for Medjai to encounter pathological cases for which generating a proof is very challenging. Time permitting, though, later on in the talk, I'll show you a small optimization that Medjai performs in order to actually scale to these pathological cases in practice. Now, to understand how Medjai is useful practically, let's take a look at the transfer function you see here, written in the Cairo language. At a high level, we want this transfer function to increase the destination balance and decrease the source balance by a specific amount. And abstracting even further, we want the balance of destination to increase and the balance of source to decrease. It makes sense for a transfer function. So to use Medjai, we can write a specification that says exactly what I just said in English and pass it into Medjai along with this program. We'll run it, and for this case, Medjai actually finds that the specification does not hold. When it does so, it will give an example indicating how the bug can be triggered. Understanding this bug requires a bit of understanding about how Cairo specifically represents uint 256 values. Since Cairo is a language for zero-knowledge smart contracts, it uses a field element data type as a primitive, called a felt here. Field element data types are integers in a field whose prime is about 2 to the 252. So you'll notice that it's not quite big enough to hold a uint 256. Instead, Cairo represents uint 256 with two felts, one for the low bits and one for the high bits. And here you might see where the problem starts to arise. There are actually uint 256 values that are invalid, specifically when either the low or high bits is greater than 2 to the 128. However, the subtraction and addition functions you see here actually assume that the amount is well formed. Thus, Medjai can find a counterexample by creating an ill-formed uint 256. And in this example, this is not something that the developer realized initially. However, using this counterexample, the developer can actually adjust their code and fix the bug. Then, in order to determine that their fix was actually correct, they can take that same specification they had before and rerun Medjai. In this case, the bug is actually fixed, so Medjai reports that the program is verified. And in this case, the guarantees here are a bit stronger than the guarantees you would get by running a fuzzer and not finding any bugs. Here, Medjai is saying that for this specification, there are actually no inputs that invalidate the specification. Okay, so that's it for the overview. But in the rest of this talk, I'm going to highlight 3 key components of Medjai. First, we're going to talk about how to actually specify correctness in the V language. Second, we're going to talk about how symbolic execution works at the core of Medjai. And lastly, if we have a little bit of time, I will briefly discuss an optimization that Medjai uses. All right, first off, let's talk about how Medjai users can actually specify correctness. Users specify correctness in a language called V, which is a declarative high-level language designed at Veradice for expressing program correctness across a wide variety of applications. Because of these goals, V is both blockchain and language agnostic, meaning that V specifications can apply to this wide variety of applications. Perhaps even more importantly, these features mean that our tools can take specifications in V and, this means that our users can write specifications in V and apply them across our various tools. For example, if you write a specification in V to use with Medjai, you'll be able to immediately reuse that same spec to run our Cairo fuzzing tester. So how do we actually write specifications in V? Well, specifications in V are written using in the form of statements. Statements are composed of 3 parts: an action, a target, and a property. Actions specify what program behaviors should be considered in the specification. For example, the action called finished specifies that only transactions that complete successfully should be considered. Second, targets tell the tool which transaction to execute. In our previous example, this would be the transfer function. Finally, the property itself specifies the condition we want to check, or the desired state of the blockchain after the transaction. Slightly more complex properties can be described as pre- and post-condition pairs. These 2 conditions are properties that should hold before and after the transaction respectively. More specifically, the specification here asks the following question. Assuming the precondition holds before the transaction, does the postcondition hold after the transaction executes according to the action? Now let's take a look at how we can use V to write our specification from the previous example. For the postcondition here, you can see that we basically copy and paste what we had before. Very straightforward and very similar. The action we want to consider here is going to be finished because we want to consider successful transactions. And probably obvious to most of you, the target is going to be transfer because we want to consider the transfer function. But we can actually add a bit more detail by using that pre and post condition structure I showed before. Specifically, we can consider an arbitrary address called other and say that this other address should be distinct from both the source and destination. In this case, the transfer function shouldn't affect the balance of other at all, as we specified here. And that's it for writing V specifications. So now I'll move on to how symbolic execution works. So for understanding symbolic execution, I'm again going to use that same example from before. And we're going to start with just how a concrete execution looks. So I'll try to go pretty quickly because I'm sure a lot of you understand how concrete program execution works. Specifically, we're going to start with a starting state that I just show a snapshot of here. And we're going to go step by step through the program. So first, we'll check for the validity of the amount. Sure enough, this amount is valid. So we're going to step to the next state. Once we reach the block that subtracts amount from the source, we're going to perform that by updating the state. Here you can see that the balance for source has been updated. And then lastly, the block that adds amount to the destination balance is going to perform very similarly. We're going to take that state that we got before and update it. And now that we're at the end of the program, what we get is an ending state. Pretty straightforward. So symbolic execution is going to work in much the same way, except instead of concrete numbers you saw there as part of the state, we're going to use symbolic values. These symbolic values represent multiple concrete values that could be in the state at runtime. And importantly, though these values are symbolic, the actual types of the state variables still stays the same. So what do we do now with this symbolic state starting execution? Well, when we perform this check for validity, if the amount is not valid, we stop execution. So when we update our state, we include now this precondition that says the amount should be valid. And why do we do this? Well, it's because if the amount was not valid, we would not continue along this branch of execution. In general, this path condition, here I call it a precondition. I'll call it a path condition from now on. It describes the properties that must hold to reach this part of the program with this state. We can continue in a similar way to concrete execution here. But we perform these operations over the symbolic values of the state. Here, we perform the subtraction on the source balance using our symbolic amount. Similarly, we're going to take the result of that subtraction, which is our intermediate state here, and plug it into the next block, the addition, which gives us this final state here, with both the balance and with the balance for source and destination updated based on the amount. After we do this and get our final state, we can check the post condition of our specification with an existing satisfiability solver. Specifically, we'll ask this solver if any instantiation of these symbolic values can possibly invalidate our property. If not, then we know that there are no bugs with regard to this specification. Okay, in the last minute or two, I'll briefly go over an optimization that Medjai uses to scale in practice. In the previous example, you might have noticed that the program we were looking at was fairly straight line code. However, let's consider how symbolic execution handles the branching program to the left. We'll first consider the case that takes the branch and update the state like so. Then separately, we have to consider the else branch, so the state's not updated. Following from here, we need to handle the second if for each of these cases, which means we branch based on the first state, and we additionally branch based on the second state. As we continue, you can see how the number of possible states we must consider grows exponentially. For this reason, Medjai takes advantage of an optimization called state merging. Specifically, after a branch, Medjai merges the two resulting states into one. Symbolic execution can then continue from this point. And you'll notice that the state here actually gets a little bit more complex. So the solving time may increase a bit, but it's worth the trade-off to avoid this exponential blow-up in state exploration. And that's it for Medjai and how Medjai scales to real-world programs. So please let me know if you have any questions.
All right, 1, 2.
Hi, nice talk. What is the status of Medjai development? Because in the last 10 months, you don't have any activity on GitHub. And your examples are about Cairo 0. What about Cairo 1?
Yeah, that's a good question. So we have a both public and private version of Medjai right now. So figuring out how to schedule updates for that is definitely a point of interest. And yeah, you are great to notice that the examples I gave are Cairo 0. That made it a little bit easier to show the examples, but Medjai actually works at the bytecode level, and this stays the same through Cairo 1.0, Cairo 2.0. So Medjai still works for those new versions. It is true that the new versions of Cairo, some bugs might not be as likely for developers to write because it's just a little bit easier to program. But fundamentally, the same properties that I described still hold. Thanks for the question.
Any other question? Yep.
Thank you for the talk. Is your technique sound for programs with loops?
Yeah, that's another good question. So for programs with loops, symbolic execution is going to differ. Basically, you can't use symbolic execution if your loop is unbounded, right? For example, if I take in an input and I want that input to be symbolic, and I also loop based on that input, you're not going to be able to complete symbolic execution, right? However, if you have loops that you can provide concrete bound for, then this technique will be able to scale and will be sound. Yeah, thanks for that question.
Somebody else? Yep.
Will have to help me out. Thank you.
Hey, thanks for the talk. Can you comment on the expressiveness of your language and how much did you manage to have developers writing specs?
Specifically, so just to repeat the question, how expressive is the V specification language? And the answer is we've designed the specification language to be as expressive as possible. The goal here is that programmers should be able to express any type of functional correctness. Additionally, what I didn't describe here is that V also allows for temporal logic to be expressed. The reason I didn't mention it is because this is not something that Medjai supports, but it is something that other tools that Verdice is making does support. So yeah, to answer your question, developers are able to write V, I think in my opinion, in a pretty straightforward manner, but obviously I'm a little bit biased. And we've designed it to be as expressive as possible.
Any other question? Yep. All right.
Can you express interactions between multiple transactions? So can you somehow chain the transactions and have a state followed in between them?
Yeah, that's a really great question. And that's not something I elaborate on the talk just for simplicity. But you saw how you can have a single V statement with the action, the single transaction, and the specification, the condition, right? If you want to express what you're talking about, multiple transactions in sequence, all you do is use multiple V statements in sequence.
Any further questions? Oh, all right. Thank you then.
Yeah, thank you.